Section 5.1 was about discrete distributions in general. In this one, we've got a specific discrete distribution that comes up an awful lot, which is called a binomial. And if you think back to section 5.1, usually discrete variables have a finite number of possible values. And here, if you're thinking binomial, bi is 2, are there going to be 2 possible values? That's an excellent thought, and the answer is sort of. This first thing here, a Bernoulli distribution, that has 2 possible values, and a binomial is sort of built out of a bunch of Bernoulli variables. So we have to kind of build our way up to the binomial a little bit. But with the Bernoulli, that's where you have a single experiment that has 2 outcomes, success and failure, just sort of generically. So the reason success and failure are in quotes there is because that's the kind of general terminology used just to differentiate the 2 outcomes. So it could just as well be heads and tails, and that's sort of the classic example of something that would be a Bernoulli random variable, is what you would get if you tossed a coin, because that's got 2 possible outcomes. And then you would view maybe heads as success and tails as failure, or vice versa. The important thing is that we just kind of have that general idea of there are 2 outcomes, so success typically being the one that you're interested in and failure being the one that you're less interested in. And success doesn't have to be the good thing, because it could be something like what's the chance that someone develops cancer, right? Then the outcome that you're interested in would still be your success, but that's not going to be the good outcome there. So the success doesn't always have to be the thing that's the good thing. And the way this is typically written out is if success is denoted by a 1 and failure by 0, you think, oh, now this looks like it's binary if it's all 1s and 0s. And I suppose a Bernoulli kind of does look that way. And also it would be customary to label the corresponding probabilities using the 1 and the 0. So the probability of success you could then write as the probability that x equals 1, and the probability of failure you could write as the probability that x equals 0. All right, then if P is the probability of success in a single Bernoulli experiment, then the probability of failure would have to be 1 minus P, right? Because when you add these together, you'd have to get 1. There are not going to be any other possible outcomes here. So if there are only 2 possible outcomes, when you add the 2 probabilities together, you got to get 1, right? So if P is 0.6, then 1 minus P would be 0.4, and that works, right? They add up to 1. Right, that's the idea. And a lot of times, this is a very common textbook thing because it makes the formulas easier to write out, that 1 minus P is written as Q. So I'll throw that in when we get to the binomial formulas. So what a binomial distribution is, as opposed to a Bernoulli, it's instead of just one Bernoulli experiment, what if it's done over and over again? So instead of flipping a coin once, what if you flipped a coin 8 times, let's say, right? Just 8 repetitions of flip the coin. And so you have some number of repetitions, and the repetitions are all independent of each other. That matters an awful, awful lot. So this right here, without this, it gets a lot more complicated. So yes, we need it here to get this to work. It's doable without that, but it's really hard, and it's not really a binomial anymore. So yeah, we're going to need this piece. So n, the number of repetitions, is typically thought of as being the number of trials. And that's usually how it's written, like in textbooks and things. So number of trials, number of repetitions, same thing. And then if we're going to have n Bernoulli experiments, then each one, or each trial, would have its own Bernoulli random variable. So then we can just say, well, then there would be an x sub 1, and x sub 2, and x sub 3, up to x sub n, right? Since there should be n of them if there are n trials, right? So like if n is 8, then you'd have x1, x2, x3, up to x8, right? You have one Bernoulli random variable for each trial. And so just like before, we're going to assume that the probability of success in a single trial is p. Like every single time, like that would stay consistent. So like for x1, that's what it is, for x2, for x3, and so forth. And that, like without that, you would again get something extremely complicated that would no longer be a binomial. All right, so then this is what we're actually going to do. we're going to end up building a new random variable x where you basically just take all of the Bernoulli random variables and add them together. So just like it is here, x1 plus x2 plus x3 and so forth, up to plus xn. And if you want to be fancy and write it with the summation notation with the capital sigma, you can. If you're not used to this notation here, don't worry about it, but it is shorter, right? And that's why people use it. It compresses stuff. So the big capital sigma just means sum, and then the indexing from I equals 1 up to n would mean you'd have x1 plus x2 plus x3 up to eventually plus xn. All right, so if that's what x is going to be defined as, where you just add all these Bernoulli variables together, to figure out the possible outcomes, first just think about what you would get for any one of these, like for x1 or x2 or whatever. The only possible outcomes for x1 are 0 and 1. Right? 0 for a failure, 1 for a success. Same thing for x2, same thing for x3, same thing for x4. So the possible outcomes, so the smallest would be 0, which is what you get if they're all failures, right? If you just had 0 plus 0 plus 0 plus 0 plus 0, you would end up with a 0, right? If you just add a bunch of zeros together. So all failures. And then the biggest would be if you had all successes, because then these are all going to be 1s, right? You have a 1 for x1, a 1 for x2, a 1 for xn. So you'd have 1 plus 1 plus 1 plus 1. You'd have n of them. So the largest would be n, which is what you get if they're all successes and you just have a bunch of 1s added together. And then every integer in between you could get. Right? Because let's say n was 8, and then, well, what if you had 5 successes and 3 failures? Okay, well, that's 5 1s and 3 zeros added together, so that's just 5, right? So the possible outcomes, you could get 0, you could get n, and you could get any integer in between. So 0, 1, 2, 3, and so forth up to n. So what is x counting? Well, it's counting the number of successes, because every time there's a success, you're adding in a 1, right? So if you want the probability that x equals 1, that's the probability that you get exactly 1 success out of however many trials you're going to do. If you want the probability that x equals 7, you want the probability of exactly 7 successes out of however many trials you're going to do. So what is x counting? X is counting the number of successes. And if this part makes sense, right, and it's the number of successes because every time you have a success, you're going to add in a 1. Every time you have a failure, you're going to add in a 0. And then algebraically, adding a 0 doesn't really do anything, right? So it's counting the number of successes. And if this part here makes sense, I think the binomial formula that we're almost up to, we got to go through a couple other things. But I think when we eventually get there, then that's going to make sense too, which would be great, right? That would be ideal. All right, so we're going to run into a little snag here, but we've got a fix for it. Suppose we want to find the probability of 3 successes and 5 trials. And to do that, we'd have to know how many possible arrangements there are of 3 successes and 2 failures, because the order doesn't matter, right? It's just, you got 5 trials, what's the probability of 3 successes? Maybe it's 3 successes followed by 2 failures. Maybe it's 2 failures followed by 3 successes. Maybe it's success, failure, success, failure, success, right? That's 3 successes and 5 trials. So how many different ways can you get that? Well, we could write them out. And I'm just going to use S's and F's for successes and failures rather than 1s and 0s. But you could have this, right? 3 successes and 2 failures. Or you could have success, success, failure, success, failure. You could have success, failure, success, success, failure. You could have success, failure, success, failure, success. You could have success, failure, failure, success, success. And you could have success, success, failure, failure, success. Those are all the ones that start with an S. So this is kind of a trick that I'm doing right now. Don't worry about having to reproduce this. You're never going to have to. The point that I'm trying to make is that this is not the best way to do it. But if you start with an F, you could have both failures and all three successes. And failure, success, failure, success, success, failure, success, success, failure, success, or failure, success, 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 failure. That's it. So there are 10. And the way that you get all 10 of them, like the way that I got them, it's sort of like a mnemonic trick. Like what I'm doing, like if I started off here, notice how I first start moving the first F one step at a time. Then I start moving the second F one step at a time. But I kept the S out front. And then starting with an F, if I just said, okay, if we had the two Fs, and I start moving that one at a time. So it's a trick, kind of, to get all of them. But this is not what we're going to do. Because even here you go, that doesn't look simple, and these are little numbers, right? 3 successes and 2 failures. These are little numbers. What if it was like 26 successes and 14 failures or something like that? It would be crazy. You'd have these strings of 40 with 26 S's and 14 F's in there, and you have to get all of them. It would take forever. Even if you used all the right mnemonic tricks to get the list, that list is extraordinarily long. So we need a better way. So that's what it says here. We need a quick way to do this, to count how many different ways you could have K successes and N trials. So like here, how many ways you could have 3 successes and 5 trials. But to do that, we have to use something called a combination. I guess if you've taken Math 142, this would come up in there. The notation is slightly different, but it's the exact same thing. And if you've had it before, when you see the factorials right here, you're like, oh yeah, I know what this is. The usual way to write it is actually like this first one. So that notation where it's not really a fraction, you have one number over another, but there's no horizontal line in between them. But within those parentheses, that's usually how it's written, or sometimes it's written with a C. If you have a calculator, like a TI 8384, I think it's in the 86. I could check because I have an 86 sitting right here. So let's see, is it in the 86? Yeah. So like in the math menu, and then if you go to prob, there's something that says NCR. That is the combination, and that kind of looks like this notation right here. It's just using an R instead of a K. But then it expands out into factorials, and just by definition, n factorial is the product of descending integers until you get down to 1. So like 3 factorial is 3 times 2 times 1. Or 5 factorial is 5 times 4 times 3 times 2 times 1. That kind of thing. And then 0 factorial by definition is 1, not 0. So if you're going to do these manually, do not forget about this, because this is the one that everybody kind of forgets at some point. Because it sort of intuitively feels like that should be a 0, not 1. But if it's a 0, you would get things that are undefined that are clearly defined. So it's 1. And the way that you read it out loud is as n choose k. So like 5 choose 3 or 10 choose 7 or something like that. And then if you have a TI-84 Plus or an 86, since I just checked, or an 83, because the 83 and the 84 are the statistics calculators, so they definitely have this on there. So the NCR function would do it, and you put the n, whatever your n number is, and then NCR, and then whatever your k is. So if you wanted 5 choose 3, it's 5 NCR 3. Or if you wanted 10 choose 7, it's 10 NCR 7. So if you want to use your calculator to do it, you can, but I think it's worth seeing how this actually is done manually. So we're just going to worry about the combinations first, and then we'll get into the binomial probabilities. But if you're going to rewrite this, so here n is 8 and k is 5, right? So if you're going to expand this with factorials, what you'd end up with is 8 factorial over 5 factorial, right, since 5 is k, but then n minus k is 3 because it's 8 minus 5, right? So n minus k is 8 minus 5, so we multiply by 3 factorial. And if you expand these all the way out, then 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then in the denominator, 5 factorial is 5 times 4 times 3 times 2 times 1. And then 3 factorial is 3 times 2 times 1. And this is how many ways can you do something, right? How many ways could you have, I guess, 5 successes and 8 trials, or 5 successes and 3 failures, if you want to phrase it like that. So this should be an integer, right? Like it should simplify down to an integer. There is, I don't want to say there's a trick, but there's a better strategy to simplifying compared to other things that you could do. And what that is, and you can kind of see it here, you could always immediately cancel out one of the factorials and then just kind of piece by piece do what you can with the other. Get rid of the big one on the bottom. So like how here I've got a 5 factorial and a 3 factorial. 5 factorial is bigger. And what I'm going to do is I'm going to say, I'm going to do this in a different color just for effect, but I got a 5 factorial right there. I got a 5 factorial right there. Done, right? Just cancel the big factorial out entirely. And then other than that, just do whatever you can do. So 3 times 2, because you should be able to cancel everything in the denominator, right? If you're supposed to end up with an integer at the end of this thing, when it's all simplified down, you have to be able to cancel everything in the denominator to get there. So 3 times 2 is 6. So I'm just going to say 6 there, 6 there. And so then what you're left with is 8 times 7 over 1. But 8 times 7 is 56. So yeah, we got an integer. All right, well then what about this next one? 12 choose 4. So n is 12, so we got a 12 factorial on top. K is 4, so we got a 4 factorial, but then n minus k is 12 minus 4, which is 8. So 4 factorial times 8 factorial. The other way to look at it is that the n minus k, it's like 4 plus 8 would add up to 12, 5 plus 3 add up to 8, right? So you could look at it that way too. There is a way to do this where you don't have to write everything out, and I'm not going to because 12 factorial is really long, and I want to show you how to do this because then it'll save you time too. I'm looking at these down here, and I go 4, 8. 8 is bigger. I'm going to get rid of the 8 factorial first. And notice where it is. It's at the end of the big factorial that's in the numerator. So watch what I'm going to do here. I'm not going to write out the whole 12 factorial because I know my first step is to get rid of the 8 factorial. And really the 12 factorial is 12 times 11 times 10 times 9 and so forth all the way down to 3 times 2 times 1, right? But I'm not going to write the whole thing out. I'm going to write this as 12 times 11 times 10 times 9 times 8 factorial. So why did I stop it here? Because I'm just going to cancel the 8 factorial anyway. And then the 4 factorial, I guess I might as well write that one out. So 4 times 3 times 2 times 1. And then the 8 factorial, I'm just going to leave as an 8 factorial. Because what am I going to do? I'm going to cancel those 8 factorials. So you can write that out all the way if you want to. But if you know already in the back of your mind you're getting rid of that big factorial, just write out the factorial in the numerator so that you're pulling numbers off the front until you get down to that factorial that you're going to cancel out. And then you go, well, wait, if I'm going to cancel this anyway, immediately, I don't need to write this whole thing. And that's true, you don't. So this is how I would do it. And then other than that, you do what you can. So 4 times 3 is 12, so we can cancel those. And then 2 goes into 10 5 times. Right, so it looks like what we're going to get in the numerator is 11 times 5 times 9 over 1. So let's see, that's 45 times 11. That's 450 plus 45, which is 495. So there we go, 495 for that one. All right, next one, 7 choose 6. All right, if we write that out, as factorials, we're going to have 7 factorial over 6 factorial times 1 factorial. Clearly, we're getting rid of the 6 factorial, right? So you can do the same move we did in the last one and write the 7 factorial as 7 times 6 factorial instead of 7 times 6 times 5 times 4 times 3 times 2 times 1, because we're going to get rid of the 6 factorial in this next step. Anyway, then 1 factorial is just 1. So this is just going to be 7. Right? Because what am I going to do here? I'm just going to say, cancel those 6 factorials. And so then we're going to end up with 7 over 1, which is 7. In this one, you could actually reason your way through it as well. Because 7 choose 6, what that would tell you is how many different ways you could pick 6 things out of 7. But if you're picking 6 things, you're leaving 1 out. So how many different ways could you leave 1 thing out? Well, you could leave out the first or the second or the third or the fourth or the fifth or the sixth or the seventh. 7, there's the answer. So the ones that are like this, where like 7 choose 6 or 10 choose 9, where the k is 1 less than n, are going to work that way. But so would anything choose 1, right? Like what's 5 choose 1? It's how many different ways could you pick 1 thing out of 5? And there are 5. You could pick the first thing, second, third, fourth, or fifth, right? What's 10 choose 1? It's 10, because how many different ways could you pick 1 thing out of 10? Well, you got 10 things, so there are 10 different ways you could pick one of them, right? So there are some where you can kind of reason your way through it without actually doing the math. This would be another one. And I'll show you what happens if you do the algebra, but this one is actually probably easier to think of without it. So you could write this as 4 factorial over 0 factorial times 4 factorial. But 0 factorial by definition is 1, and clearly you're just going to cancel these 4 factorials, right? And I guess I've been doing this in red, or kind of like a, I don't know, like a maroon more than a red. But yeah, you're going to cancel those out, and you're going to say, well, this is 1 over 0 factorial, but 0 factorial is 1, so this is 1 over 1. So it's just 1. All right, well, I said you could do this without the math. Sure. What is 4 choose 0? It's how many different ways could you pick or choose 0 things out of 4? There's 1. You don't pick any. That doesn't have any other arrangements, right? There is one way to do it, though. And anything choose 0 is like that. You know, 45 choose 0. How many different ways could you pick 0 things out of 45? 1. You don't pick any. That's the only way you can do it. And then the other side of that is, what would be 4 choose 4? That's also 1. How many different ways could you pick 4 things out of 4? 1. You just pick them all. That doesn't have any other arrangements, right? So 4 choose 4 is 1. 13 choose 13 is 1. 63 choose 63 is 1, right? Anything choose itself is always going to be 1, and anything choose 0 is also going to be 1. And you could kind of see why algebraically, too. Because what's the difference algebraically between 4 choose 0 and 4 choose 4? The order of the factorials in the denominator is reversed. But multiplication commutes, right? If you change the order, you get the same expression, right? 3 times 2 is the same as 2 times 3. Same thing here, right? This is the same as 7 choose 1, because 7 choose 1 would look just like this, except it would be 1 factorial times 6 factorial in the denominator, right? So sometimes you can recycle combinations that you've already figured out because of that, too. Because multiplication commutes. So even if you had something weird, like if you had 20 choose 7, but then later you needed 20 choose 13, those are going to be the same. So there are things like that that once you start doing a few of these, you start to notice and you go, there are, little, I guess, wily veteran type tricks that you can use once you kind of know your way around this a little. But this is the thing that we've been working up to. So for a binomial probability, this is the function that you can use. So the probability that x equals k, where k is some number of successes, n choose k to cover like all of the different possible arrangements of successes and failures, right? That's what that's for. Times p to the k times 1 minus p, or q, if you want to write that as a q, raised to the power of n minus k. So this part here, if you ignore the combination, it's the probability of success raised to the number of successes times the probability of a failure raised to the number of failures, right? Because if there are k successes, there are n minus k failures. And then, so this takes care of the successes, this takes care of the failures, then the n choose k takes care of how many different arrangements you would have, right? So it's got to be multiplied in there too. And then, as before, p is the probability of success in a single trial, k is the number of successes, n is the number of failures. So let's actually do this, where we're getting some concrete numbers in there. So with this example, it says based on past data, 30% of the oil wells drilled in an area having a favorable geological formation have struck oil. And a company has identified 8 locations with that formation. So what they're going to do is they're going to drill a well on all 8 sites. And since the locations are really far apart, we can assume independence. Like it says there, it's safe to assume the chance of striking oil at any location is independent of the chance of striking oil at any of the others. So in this context, success is striking oil, failure is not striking oil. So what's the number of trials? Well, basically the thing that's being repeated is drilling for oil, right? That's being done 8 times because there are 8 different locations. So the number of trials, n, that's going to be 8. And then the probability of success in a single trial, well, 30% when you have the favorable geological formation. So you got to rewrite that in decimal form. So 30% would convert to 0.3 or 0.30. All right, we're just about there. And let's see. First, we want the probability that exactly 3 of the 8 wells strike oil. All right, so that would be the probability that x equals 3. And if you follow along with the formula on the previous page, if n is 8 and k is 3, we should have 8 choose 3 times probability of success in a single trial, which I'm just going to write it as 0.3 to save space, just without having those extra zeros in there. So it would be 0.3 to the third, and then the probability of a failure would have to be 0.7, right? 1 minus 0.3. And then the number of failures would have to be 5, right? If you have 3 successes in 8 trials, you got to have 5 failures, because the number of successes plus the number of failures should add up to the number of trials. Or I guess if you want to do it directly using the formula, where that 5 comes from is 8 minus 3, right? So the only thing I think you could simplify by hand would be that combination. We actually already have it. I think we did it. Let's see if I go up here. I believe it's actually, yeah, it is actually an 8 choose 5. But look at the only difference between 8 choose 5 and 8 choose 3 is that the factorials in the denominator are going to show up in the opposite order. So we get to recycle work that we already did, so that's nice. But if you did write it with factorials, you'd have 8 factorial over 3 factorial times 5 factorial, and then times 0.3 to the third times 0.7 to the fifth. But we already know what this quotient of factorials is going to turn into, right? It's going to turn into 56 because that computation is identical to 8 choose 5, except that those factorials show up in the opposite order. So you'd have 56 times 0.3 cubed times 0.7 to the fifth. And I think this is where you probably want a calculator to do this part. And what you end up with, if you put this into a calculator, is at least to 4 places, 0.2541. Right, so about 25%, a little bit bigger. Okay. So for anywhere, it's just find the probability that x equals, here it's 3 or x equals 2 or x equals 5 or whatever it is. It's basically what we just did there, right? I guess you'd have a different k, which would affect a couple of things, but it's that concept. However, a lot of the time, instead of the probability of an exact number of successes, we want a range. So this one is a range because it's what's the probability that at least 1 strikes oil. At least 1, I think you would write like this. Right? And you could do this directly. We're not going to. And this is why. Because what's going to satisfy this inequality? Well, we're digging 8 wells. So 1 is at least 1. So is 2, 3, 4, 5, 6, 7, and 8. So we could do this as the probability that x equals 1. Plus the probability that x equals 2, plus the probability that x equals 3, and so forth, all the way up to the probability that x equals 8. What's the problem? That's long. Look how long number 1 is. That's not terrible, but if you had to do 8 of them, right, 8 things that were this long, then that's kind of terrible. So we're going to work around this. And the way that you can work around it is if you have to get a probability of a range of values like this, and it looks like it's going to be really long, the best thing to think about is the complement. Because sometimes if the direct probability is long, then the complement's short. And here, the complement is short. So Or, since we're not actually going to do it this way, what we're going to do is we're going to say that this probability that x is at least 1 is 1 minus the probability that x is strictly less than 1. Right? That's the complement. Right? Every possible value is either greater than or equal to 1 or strictly less than. Right? There's no overlap, and that would cover everything. But how many possible numbers of successes are less than 1? 0. And that's it. Right? Because we can only have integer values and we can't have negatives. Right? You can't have a negative number of successes. That doesn't make any sense. So really, this just comes down to 1 minus the probability that x equals 0. So look, if you use the complement here, you only got to figure out 1 probability instead of 8. This is way better. So that's what we're going to do. And we're going to say, all right, well, then this is 1 minus, and then the probability that x equals 0 would be 8 choose 0 times 0.3 to the 0 times 0.7 to the 8th. And this is actually pretty easy to simplify because 8 choose 0 is 1, right? How many different ways you can pick 0 things out of 8? 1, you just don't pick any. 0.3 to the 0 is 1, right? Because any non-zero number raised to the 0 power, just from algebra, automatically that's a 1. So look at what we're going to get here. Like this is going to fold up nicely. We don't have to do very much computation at all. So we'll have 1 times 1 times 0.7 to the 8th, or just 1 minus 0.7 to the 8th. So I guess then you'd have to put that into your calculator, and what you get is 0.9424. At least to 4 places, that's what you get. All right, so sometimes the complement ends up being helpful, right? That's the point of this question. And then number 3, we can't actually use it, sadly. So the probability that more than 5 wells strike oil, so more than 5, that would be the probability that x is greater than 5. Strictly greater, right? Because more than has to be bigger, can't be equal. All right, well, if we did this directly, you'd have the probability that x equals 6, 7, and 8, and you have to figure those out and add them together. If you use the complement, it's actually longer, because then the complement would be less than or equal to 5, and you have 0, 1, 2, 3, 4, 5. That's 6 things. We should just do this one directly, because doing 3 things is better than doing 6 things if we're going to end up in the same place anyhow. So we'll just do it directly, and we'll get the probability that x equals 6 plus the probability that x equals 7 plus the probability that x equals 8. And then we can just use the formula 3 times and say, well, then this will be 8 choose 6 times 0.3 to the 6th times 0.7 squared. And then for the next one, the probability that x equals 7, you'd have 8 choose 7 times 0.3 to the 7th times 0.7 to the 1st, right? 8 minus 7 will give you that 1. And then plus 8 choose 8 times 0.3 to the 8th, and then times 0.7 to the 0. Okay, well, let's see. Since we don't have a ton of space here, and this video ends up being really long anyway, I'll just tell you what the combinations are, and if you want to check them later, you can. I think that would be a good idea. 8 choose 6 is 28. So we'll have 28 times 0.3 to the 6th times 0.7 squared. 8 choose 7 is 8. So 8 times 0.3 to the 7th. And then I guess just times 0.7, right? 0.7 to the 1 is just a 0.7. And then here, 8 choose 8 is 1 times 0.3 to the 8th, and then just times 1, since that's what 0.7 to the 0 would be. So what are we going to get? Well, if you go to 4 places, this first one ends up being 0.0100. The second one is 0.0012. And then the third one ends up just being 0.0001. And if you add those together, you get 0.0113. And that is the answer. And here, admittedly, I think we're kind of pushing up against the notion of, wouldn't this be easier with StatCrunch? instead of having to do a whole bunch of these. Maybe if it's a single binomial probability, then doing it by hand's not a big deal. Or maybe if it's just a couple. 3, you go, that feels like a decent amount of work. And, what if it was something where it was like, what's the probability of 8 successes in 20 trials? Or I guess, no more than 8 successes in 20 trials. The best way you could do that, if you're going to do the whole thing manually like this, would involve figuring out 9 individual probabilities, and that's a little much. So we're almost up to the StatCrunch stuff. We just have one more thing to go through, which is center and spread. This is pretty easy for a binomial. One thing I will say, there's a huge trap here. Don't fall into it. It's not wrong, but it creates an awfully large amount of work that you don't really have to do. Because a binomial is a discrete variable, the formulas for a general discrete distribution work. So like if you wanted to find all of the probabilities of the specific numbers of successes and make a table like we had in section 5.1 and then get the expected value from there, you can do it, but that means you got to find a lot of individual probabilities. And look at what happens otherwise. Like, you could do all that work if you really felt like it, or you could just do that. N times P. And you're done. And the reason that works, it's because of independence, where the probability of success in a single trial is P, but if they're all independent in their N trials, then your expected number of successes is just number of trials times P. And that's it. So, yeah, that's the way to go here, I think. So in the oil example, the expected value, or the expected number of wells to strike oil, if it's N times P, N was 8, P was 0.3, 8 times 0.3, that's just 2.4. Done. You can do that the long way if you want to. I don't want to. So I'm not going to. And then what's the standard deviation? Well, if you want the standard deviation, it's right up here, right? It's just the square root of N times P times Q. So the standard deviation of X would be the square root of NPQ. But then we know N is 8. We know that P is 0.3, and if P is 0.3, Q is 0.7. So then what you would get here, if you, I guess, did the multiplication, then took the square root or whatever that is, you should get 1.296, roughly. At least to 3 places, right? So doing those manually, that doesn't feel like a big deal, and it's not. At least if you do it this way, right? Because they're binomials, you could do the expected value like this and the standard deviation like that. If you did them the long way, where you got all the individual probabilities first, then it probably doesn't feel all that convenient, I suppose. All right, so then StatCrunch. How do we do this in StatCrunch? Well, there's that Stat button. So under Stat, you go to Calculators, which is right up at the top of the menu, and then select Binomial. So I can show you. So here it is. There's the Stat button, Calculators right at the top, and then Binomials right there. Right, they're alphabetical, so it's the second one. I guess except for Custom, that's at the very end. But then you get this pop-up. And then it's kind of described here what you do with the pop-up. You specify N, the number of trials, specify P, and then you can figure out whatever probability you want. And so, yeah, this will cut down on a whole lot of work. Okay, so first things first, there is an expected value, so we don't really need StatCrunch for that. We're not going to use it. But once we get into the probabilities, we're going to... So like it says there, it's believed that about 86% of all drivers in the U.S. wear seatbelts, and suppose a sample of 50 drivers on I-10 is randomly selected. So what this is asking for is the expected value, right? How many do we expect to be wearing seatbelts? There's the red flag, right? The word expect, you go, yeah, that's an expected value. So N is 50, and then P, the probability of success in a single trial, is 0.86, right, from the 86%. So basically P comes from there, and then 50, that's the N. And so that's all we really need, right? Because the expected value, it's N times P. And then we can say, well, N was 50, and then p is 0.86 because you got to convert it to decimal form. But 50 times 0.86 is 43. All right, that didn't seem that bad. And then number 2 is what's the probability that exactly that number, so that number being the answer from number 1, right? So here this is just going to be 43. So we want the probability that x is exactly equal to 43. And if we were going to do this one manually, it's going to be, well, a decent amount of work to simplify the combination. 50 choose 43, even if you cancel out the big 43 factorial first, you're still going to have a lot of work to do. So let's do this one in StatCrunch. All right, so we got to change n. Our n is 50, so we're going to put that in there. Then our p is 0.86, so we're going to put that in there. And then we want the probability that x is equal to 43. So if I click on where this inequality is, I can change what goes in there. I want an equals, and then I want a 43. And then compute, and there it is. So to 4 places, it's 0.1606. And this graph up here, the red part shows you what probability you're getting. So here we just wanted 43, so that vertical line, that's what that represents. So we're good to go. It's 0.1606. So this just ends up being 0.1606 using StatCrunch. But then what about at least 40? Okay, well, at least 40 would be the probability that x is greater than or equal to 40, right? Because at least would include the 40, right? So for the at least, that should be greater than or equal to. If it said more than 40 instead of at least 40, then you'd get a strict greater than, right? But at least 40, this would be a nightmare by hand. You have to get 11 individual probabilities. Oh, I take that back. You have to get 10 because you already have the 43. But you know what I mean. All right, back here, I want at least 40. So let me change where this equals is. I'll change it to a greater than or equal to. And then I want greater than or equal to 40. Compute, done. 0.9176. And then here you can see, right, just to double check, like look at the picture, make sure the red part is what you want. So at least 40, we're including the 40, since right above the 40 we got that red line. And then all this over here is also what we're including. So yep, 40 and everything bigger, that's what we wanted. 0.9176 to 4 places. All right, so 0.9176. Okay. And then less than 35. Okay. So the probability that x is less than 35, this one's a direct translation, right? You don't have to say like, well, at least, what kind of inequality is that? Less than, we know what kind of inequality that is, right? It's a less than. All right. So let's do this one. We need less than 35. And to 4 places, it would be 0.0009. I think the homework sometimes, instead of asking for the answer to a specific number of places, it asks for it like with 3 significant figures. So if you did it that way, so I'll just say like with 3 sig figs, right? That's how everybody abbreviates it in chemistry. It would be 0.000927. Because if I go back here, right, you have the 92698. So yeah, 3 significant figures, you'd round off where there's that third non-zero digit, right? So 0.000927. So sometimes the homework does that, so I guess just watch out for it. You can't really tell, I wouldn't imagine, but those are little red dots right there. So less than 35, looks like we're getting what we're supposed to. The last one on this page is kind of interesting. The probability that the number of drivers wearing seatbelts is between 40 and 45 inclusively, meaning less than or equal to's. So like for A, the thing that we're getting is the probability that 40 is less than or equal to x is less than or equal to 45. So the word inclusively, right, that's the key. That's how I know that it should be non-strict inequalities. Because inclusively means include the endpoints. So include the 40 and include the 45. And how do you do an in-between? Well, if we go to StatCrunch, up here, standard is the default. But if I change it to between, there we go. Then look at this probability down here. It's set up to handle this kind of interval that we've got. So 40 less than or equal to x less than or equal to 45. And what we're going to get is, at least to 4 places, 0.7648, it looks like. All right, so right here, that's going to be 0.7648. And then the other one, strictly between 40 and 45. That's where you would not include the endpoints. So probability that 40 is less than x is less than 45. There's a slight issue, which is if we go back to StatCrunch, you can't adjust the inequalities here. So that means that if you have a compound inequality like this, a between inequality, you've got to adjust what you have so that it has less than or equal to's in it. So since you can only get integer values, then the probability that x is in between these strictly, we can then rewrite using the next integers over. So being greater than 40 is the same thing as being greater than or equal to 41 if you can only get integers, since there are no integers between 40 and 41. And you do the same thing on the other end, because being less than 45 would be the same thing as being less than or equal to 44. Since there's nothing between 44 and 45 that you could have, right? I mean, if it's got to be an integer, there's no integer in between those numbers. So what you would do here is rewrite this as the probability that 41 is less than or equal to x is less than or equal to 44. So I'm making an adjustment on both inequalities. I'm saying greater than 40, same thing as greater than or equal to 41. And then less than 45 is the same as less than or equal to 44. Since you've got to get integers, right, those are the only possible values since it's the number of successes, right? That's a count. It's got to be an integer. But then this has less than or equal to's in it, so we can actually use StatCrunch. And if we do that, then this needs to be a 41. Then this here needs to be a 44. If we compute it, and then here you can see, this is where the picture helps. Because then you look at this, you go, okay, yeah, the red parts strictly between 40 and 45, right? The 40 and the 45 themselves aren't included because we got black lines above them, but everything in between is red. That's what you want. So yeah, looks like we got 0.5649 if we're going to 4 places. So right here, 0.5649. All right. Then after that, let's see, the range rule of thumb. So just like when this came up before, a value more than 2 standard deviations away from the mean would be considered unusual. So above mu plus 2 sigma would be considered unusually or significantly high. Below mu minus 2 sigma would be unusually or significantly low. And to apply it, then it's necessary, at least here, like with a binomial to apply it, you need n times p and n times q to both be at least 5. And so for the seat belts, n times p is the expected value. We already figured that out. It's 43. But then n times q would have to be 7, right? It's 50 times 0.14. Or you could view it as that n times p plus n times q would have to add up to n. So therefore, it's 50 minus 43, which is 7. Either way. But both of these numbers are greater than or equal to 5, so we're good to go. So in the seatbelt example, would 35 be significantly low? Well, we can figure this out. We already know what mu is, because that's the same thing as the expected value, and we had computed that already. We know it's 43, right? It's n times p, but it ended up being 43. We did it on the last page. And then sigma, which would be the standard deviation, we haven't done this one yet. It would be the square root of n times p times q. So here that's going to be the square root of 50 times 0.86 times 0.14. So that's a 4, even though it doesn't really look like it. And then what that ends up being is 2.454. Actually, let me fix that thing. I do not like how that looks. Much better. Okay, so then 35 is on the lower end, right? It's less than 43. So we just have to see, is that more than 2 standard deviations away? So we just have to figure out what mu minus 2 sigma is. Well, then that'll be 43 minus 2 times 2.454. So that's 43 minus 4.908, which is 38.092. So anything less than that is going to be unusual, right? So 35 is definitely smaller, right? That's less than 38.092, which means that 35 is unusual. Unusual or significantly low. All right. And then probabilities could also be used to determine if a value is significantly high or significantly low. Assuming that n times p and n times q are both at least 5, then we can do this, where if the probability that x is less than or equal to a, if that's less than 0.05, then the value a is significantly low. Or on the other side, if the probability that x is greater than or equal to some number b is less than 0.05, then that value b is going to be significantly high. All right, so this is going back to the empirical rule. Ultimately, that's what it is, right? Because that's where when you go 2 standard deviations away in either direction, you get the 0.95 in the middle and the 0.05 and the two tails combined, right? It's related to that, right? Like, and that's why these numbers are being used, right? All of this really ties together, even though it may not look it right now. So in the seatbelt example, we have a couple of numbers where we want to see if they're significant. So would 37 be significantly low? Well, then that would be like this first bullet point where the 37 is our A. So we have to figure out the probability that x is less than or equal to 37 and just see how small it is. Okay, that's what StatCrunch is for. So I want to go back to the standard because I don't want a compound inequality, and I want less than or equal to 37. And we get 0.0179 to 4 places. Okay, so then this is about 0.0179, but that's pretty small, right? That's less than 0.05, right? So 0.0179 less than 0.05, which means that, yeah, 37 is significantly low. Significantly low. And then the other one, would 46 be significantly high? Well, we can answer that the same way. And since this one's talking about being significantly high, it's going to look like that second bullet point where we want the probability that x is at least 46. So 46 and the upper tail. So then actually going back to this one, just to look at the picture for a second. So less than or equal to 37, it's 37 and below. So it's this tail, right? So we got a red tail here. We're going to get a red tail with the 46, but it's going to be an upper tail. It's going to be a right tail. So what we're going to do here is we're going to figure out the probability that x is greater than or equal to 46. Right? We want to see if it's significantly high. So if I go back here, then I want a greater than or equal to, and then I want this to be 46. There, 0.1528. All right. So we get 0.1528. And then just to go back to the picture for a second, notice again, it's a tail, right? It starts at the 46 and includes that, but then it's everything above it as well, right? That's all in red. And this idea of using the tails in this manner, it's really big for hypothesis testing, which at this point is actually not that far in the future. And that's really what it's alluding to here, even though it doesn't directly talk about it. But then this number is not small enough to be significantly high, right? It would have to be less than 0.05, and that's about 3 times as large. So 0.1528, that's greater than 0.05, which means that 46 is not significantly high. All right, that should cover all the binomial stuff. And I know this one's really long, but it kind of has to be to talk about how to do it manually with the combinations and all that. But with the homework, really you could do it one way or the other. And I know most people are going to pick using StatCrunch to do it. I mean, it is a lot faster, right? And you can look at the picture and make sure you're getting the right thing. But if you have time, even just doing a couple manually just to make sure you're getting the right thing. Just if you know how it actually works, then when you use StatCrunch, right, it's going to make that much more reliable, right? Because once you have that kind of hands-on experience of doing a couple manually, then when you're using StatCrunch, you're going to be much more comfortable. So, like I said, I know most people are going to use StatCrunch, but I think it would be a good idea if you've got time for it to even just do a couple by hand, just to get a feel for like how the innards of the distribution work, so to speak.